Okay, this is the Chapter 5 review video. Again, looking at our table of contents. The chapter outline is the easiest way to get the big picture. Chapter 5 was failures resulting from static loading. And so we talked about static strength. We'd already mentioned stress concentrations earlier and talked about where they apply and where they don't. And the failure theories, and we're going to talk about 3 failure theories for static loading of ductile materials. That would be the maximum shear stress theory, the distortion energy theory, and the Coolmore theory. I've only given you homework on the first 2. And then we also have failure theories for brittle materials. We didn't look at those, but they're exactly the same kind of equations with if statements. And so there's really no difference in how they're used. So skipping over some of the interesting pictures. Okay. Basic idea is quite often we're going to have to design using published values of yield strength, ultimate strength, percent reduction in area, percent elongation, those kinds of things presented in Chapter A. And that's the information we're going to have. And that information was derived from a tensile test from a part that was a certain shape, certain surface finish, certain sizes, all of that kind of thing. And our part is nothing like that. And so we've got to make some kind of an inference from that data on whether or not our part is going to fail. And so away we go. This summarizes the 6 different failure theories we would see, 3 for ductile, 3 for brittle materials, but really it's going to boil down to only 2 for brittle materials in just a minute. The maximum shear stress theory is totally Mohr circle related. So let's just slide away and see if we, actually I guess we didn't draw any more circles in the notes because we've drawn them enough. But what we need to know, most importantly, for the maximum shear stress theory is that the part will fail. Let's go ahead and read this. Maximum shear stress theory predicts that yielding begins when the maximum shear stress in any element, meaning anywhere within the part, equals or exceeds the maximum shear stress that occurred in a tensile test specimen of the same material at yield. Okay, so we're always going to say maximum shear in our part becomes the same as the maximum shear stress in a tensile test specimen at yield. Now, the tensile test specimen at yield was a very simple element that only had axial loading, and that axial loading in one direction and 0 in all other directions gave us a very simple Mohr circle. It was a circle that passed through the tensile stress and it passed through 0. And so the radius of that circle is half of the tensile stress. Therefore, the shear stress at yield is equal to half of the tensile stress yield. Okay, so the radius is equal to half of the diameter. This is what was true in the tensile test. And so then we can compare our maximum shear stress to that maximum shear stress. But our maximum shear stress may have more complicated loading, and that's what leads us to these cases. And remember, very, very important, these are for plane stress, okay, where we have 0 stresses in, or we have no stresses in the z direction, no stresses of any kind in the z direction. And sigma A and sigma B, only 2 numbers, comes from the Mohr circle that we would draw from a plane stress element, and it comes from that first circle that we would draw. Of course, we would remember to draw the other 2 circles, but it's not necessary. We draw the first Mohr circle and get sigma A, which is the rightmost stress value, and sigma B, which is the leftmost stress value. And the if statements take care of the other 3 Mohr circles, okay, and will have us use the equations from the right one. If our Mohr circle is entirely in the right-hand plane, then sigma A combines with a 0 to make the biggest Mohr circle. And so sigma A over 2 would be our maximum shear stress. So we would end up saying sigma A over 2 is Sy over 2, that's shear stress in the tensile test, but we lose the 2's in this case because they just cancel out. Case 2 says A and B straddle the origin, so the sigma A, sigma B circle is the largest of the three circles. Therefore, the diameter of our circle becomes bigger than the diameter of the tensile test circle. We fail. Final is sigma A and B are both negative. Therefore, sigma B combines with the 0 to make the largest circle, and we fail whenever our sigma B is to the left of, and there's a negative sign there. You can't see it. I don't know why I'm getting these lines on the screen, but there's a negative sign right there. Okay. I just repeated the cases on this slide. This is a plot that people are fairly used to seeing, and it's a plot of on axes of sigma A and x direction stress, y direction stress, sigma A axis, sigma x axis, and a sigma, let's see, I'm having trouble writing. No, this is the sigma A axis, the sigma B axis. The boundaries we put it on it would be the yield stress boundaries. Anytime we leave this shape and go outside those boundaries, we have failed according to the maximum shear stress theory. Here's case 1 boundary, there's case 2 boundary, and there's the case 3 boundary. Distortion energy, I won't go through the explanation, but it basically says there are some stresses if we have uniform pressure or uniform axial tension, all three directions, and no shear. So all of our stresses are the same in every direction. We will change the size of the part, but we won't change the shape of the part. Therefore, we won't distort the part, and that part will be able to handle extremely large stresses without failing. So we can say that any stress state can be turned into this uniform pressure stress state, where all of the stresses are the same in every direction, plus a distortion type stress state. And so we go through mathematically and process that and see where the equations lead us. And we finally reach our von Mises equations, or distortion energy equations. We fail when the von Mises stress becomes greater than the yield stress. And here's one form of the von Mises equation written in terms of sigma 1s, sigma 2s, and sigma 3s. Those are the principal stresses from all three Moore circles that might have come from any state of stress. So if we happen to have information on sigma 1, sigma 2, sigma 3, then this is the handy equation for getting the von Mises stress. Otherwise, if we have XYZ loading in our Cartesian coordinates, then this is an equation with sigma x, y, and z, and the 3 taus in the XYZ directions. This is the full equation for the full cube state of stress, where we have done no more circles processing on it, and that gives us the von Mises stress. If we have plane stress, which means we only have sigma x, sigma y, and tau xy, then this equation simplifies down to this equation. And again, we can calculate our von Mises stress. And in every case, we go back and compare the von Mises stress to the yield stress. This is a picture that shows the distortion energy failure zone superimposed on top of the maximum shear stress failure zone. And we can see that maximum shear stress is slightly more conservative, yet at certain points there's complete agreement between the two. We also see that the distortion energy is slightly less conservative. Turns out it's just a touch more accurate, and so when we want accuracy, we can use von Mises. When we want conservativeness, we can use maximum shear stress. But the other thing is the von Mises has a smooth curve, no corners, therefore no transitions from one equation to another. It's a one equation method, and that really makes it wonderful. So it's more accurate, and there's no if statements. Makes it very, very easy to use. Those are the two methods that I gave you homework on. There's some example problems, very much like the homework that I gave you. We did talk about a load line, so I'll remind you of that because we're going to talk about it again briefly in the little bit of chapter 6 that we've talked about. Okay, so a line going through 0 through the load that we have, continuing outward, we can estimate distances of our actual loading point from the boundary relative to the length of the zero line to the point. And so it looks to me like this distance from the point to the boundary is about 25% of this original line between 0 and the point. And so I would say that the factor of safety is this total length from here to the failure boundary divided by the length from here to the point, and that's about a ratio of 1.25. To my eye, this factor of safety, this distance almost looks like it's this distance, maybe not quite. So I would say it's about a 1.8, 1.9 factor of safety. The ratio of the long line between the origin and the failure point, that line divided by the shorter line would be a factor of safety estimate. This factor of safety looks like about a 1.6 total factor of safety, ratioing the long line to the shorter line. So we can use failure diagrams, load lines to estimate factors of safety and actually do a pretty good job with it. We did mention the Coolmore Theory for ductile materials. It does lead to another set of if statements. It's with very simple equations. And if we had gotten into the, this is what, I don't know that we ever got to this picture, but it shows von Mises data sitting on top of both failure curves. Shows the von Mises data fitting very nicely here. Shows it fitting reasonably nicely here. And it shows why the maximum shear stress is a bit more conservative, because von Mises says these points are fine. Maximum shear stress says those points fail. So maximum shear stress would be just a touch more conservative. I think that's all I'm going to say about this chapter. We did have the brittle equations, but as you see, there are equations that involve the sigma A's and B's, and if statements that tell us when we may use these. So this would be a sigma A and B both greater than 0, use that equation. A and B straddle, use that equation. A and B both negative, use that equation. Nothing new and surprising at all for brittle materials. And that would be chapter, here's a flowchart that says if ductile, then do we have the same yield in tension and compression? If no, we'd use the ductile Coulomb-Moore. If yes, we choose between max shear stress and distortion energy. Whether we want to be conservative, yes, max shear stress. Conservative, no, distortion energy. So a simple table to tell us which one to use, and that would end this chapter.